In VR locomotion, the user explores a virtual environment while located in a different physical environment. It's common for the size and layouts of these environments to be different. This leads to a fundamental problem in VR locomotion, wherein an unobstructed path in the virtual world may correspond to an obstructed path in the physical world. Redirected walking helps to alleviate this problem. It works by slowly rotating the virtual environment around the user while they walk, which causes them to adjust their physical trajectory to compensate for the rotations. The end result is that we can steer the user on paths that differ from the virtual path. The speed of the virtual rotations is controlled by parameters called gains. Redirection controllers are algorithms that determine how and when to apply redirection gains to steer the user. For a given virtual path, there may be many valid physical paths that the user can be steered along. The controller tries to steer the user on the path that minimizes the number of collisions. Many controllers have been developed over the years, including steer-to-center, and controllers based on artificial potential fields or reinforcement learning. Different types of redirection controllers may operate on different assumptions that constrain their decisions. For this work, we consider controllers with the following assumptions. There is one user who is located in a physical and virtual environment. The controller can apply rotation, translation, or curvature gains. The controller makes steering decisions using only the information available on the current frame. Another common assumption of existing controllers is that the virtual environment is infinite and empty. This is usually done because the virtual environment can have one of an infinite number of layouts, so it's not feasible to test algorithms in every virtual environment. However, this assumption limits a controller's ability to avoid collisions because a large portion of information that is relevant to the locomotion problem is essentially being ignored. To get around this limitation, we leverage alignment. This is the concept of comparing the physical and virtual environments according to some common feature. Using alignment, we can compare the similarity between two environments with respect to the common feature. For this work, we compare environments according to the user's proximity to obstacles. Alignment is likely intuitive for many VR researchers, but to the best of our knowledge, this idea has not been formally studied outside of a few recent studies by Thomas et al. Now we'll talk a bit more about how alignment can be useful for VR locomotion. Consider this pair of physical and virtual environments. The positions of obstacles illustrated as black shapes relative to the user, depicted as a cursor, are different in both environments. If the user tries to walk forward in VR, they will walk into the obstacle in front of them in the physical world. Now consider this new pair of environments. Notice that the environments have different layouts. If the user tries to walk forward in this scenario, they can do so without walking into any obstacles. This is because the user's proximity to obstacles in both environments is similar on a local scale with respect to the user's position. Thus, we see that even globally dissimilar environments have local similarity and that these regions of local similarity lead to fewer collisions. Equipped with this knowledge, we developed an alignment-based redirection controller, or ARC for short. ARC compares the layouts of the physical and virtual environments and steers the user towards locally similar positions. It does this by first computing the distance to the closest obstacle to the left, right, and in front of the user. Then, the similarity of the environments is computed as the sum of the pairwise differences of these distances. ARC aims to steer the user to minimize this sum. Full details on the algorithm can be found in our paper. For example, in this scenario, our algorithm will steer the user towards the middle of the space between the left and the right walls in the physical environment. And thus, using curvature and translation gains, the algorithm is able to match the user's physical and virtual positions exactly after some time. We evaluated ARC in 3 pairs of environments, including both simple and complex environments. We compared ARC against 2 state-of-the-art controllers, steer-to-center and artificial potential fields. Here we see a simulated user being steered by ARC, steer-to-center, and potential fields in an identical physical and virtual environment. Notice that when steered by ARC, the user incurs a few collisions at the start of the path, but eventually their position in the physical world matches their position in the virtual world, and they experience no more collisions. The other controllers, however, continually incur collisions because the user's state in the 2 environments is constantly mismatched. Here we see a heat map of the user's location in the physical space accumulated over 100 different paths. Yellow regions indicate more time spent in that area, while purple regions indicate a low amount of time spent in that area. As the user travels on more paths, they are able to make use of a larger percentage of the physical space when steered by arc, while the other controllers tend to get the user stuck in pockets of space. Arc was able to avoid significantly more collisions than both steer-to-center and potential fields in every environment we tested. Full details can be found in the paper. Finally, we see that in addition to achieving significantly fewer collisions, Arc steers the user with less intense gains, which creates a more comfortable experience for the user. We showed that physical and virtual environments can be globally dissimilar but still have locally similar configurations. Through our novel alignment-based redirection controller, we showed that steering the user towards physical locations that are locally similar to the current virtual location can yield significant benefits. In particular, our algorithm achieves significantly fewer collisions, allows the user to explore a larger percentage of the physical environment, and steers the user with less intense gains. We hope that future work in this area will make use of alignment, as it has been shown to be a powerful tool in virtual locomotion. In an effort to encourage other researchers to work on this problem, we released the alpha version of Pesumi, a library for developing controllers for redirected walking. The library has a controller API which makes it easy to develop and compare new algorithms, since this is a bit of a problem in our field. It also allows you to quickly run large-scale experiments to collect lots of data. We plan to continually update this software, and we hope that others in the community can contribute as well.